Hi everyone, good morning, afternoon, 12 o'clock, good lunchtime. I hope everyone's doing okay. We have a near record low attendance. Actually, there's more people here than I thought. We've got about 5% of the course, which normally we have maybe 15% of the course. And yeah, it's good to see so many people here, given that the assessment's due tomorrow. We'll see how many of you we have here tomorrow to talk about the exam, given that the lecture kind of happens in the final hours. That wasn't by design, obviously. That's just because we've extended the due date twice now. So, yeah, I mean, just before I get into it, because we've got a couple of topics to go through today, but honestly, they're quite light, so we'll probably finish at a reasonable time. I just want to ask is, how's everyone going with everything? Most students seem to be going okay with things. I think the two themes that I see people struggling with are one is like just a couple of groups still are kind of like have questions about their iteration 2 marks, and then I see a lot of people struggling with the deployment side. And actually I wanted to chat about that quickly, because so deployment is worth a very small part of this course, right? Like it's like the project is what, 0.5%, like 50%, and then iteration 3 is 30, and then deployment is that. Okay, so it's times 100. It's worth 0.75 of a mark, right? So when rounded up, you get just 1 mark in the course. The reason I think deployment's an interesting topic for all of you is because I think it paints the picture really well about how a lot of these topics actually are a very different kind of challenging. Because like I think what happens a lot, like being very honest with you, like a lot at uni we're kind of just like, here is a nice little box and you write some Python and you print an output, and that's like what that is, right? But it's like the challenge with something like deployment is you're often using other software services, and a lot of the time when this is the case, you can't actually just Python your way through things. You can't actually just like kind of write more code to solve problems, right? Because that's kind of how you solve problems generally, right? You just like write more code. But yeah, I think these ones are particularly challenging because it's kind of like you have to get these really annoying things right. And then different groups do different weird things. Maybe some of you use a certain module. Maybe some of you change some variables in your server file. Some people use things and they don't blah, 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 blah. And it's challenging because you can't really program your way out of it. You actually just have to kind of like, progressively dig and stuff. And I think what's been really incredible for me is seeing so many people actually trawl through that. We genuinely didn't expect so many people to care about that. Given that most groups lose a lot more marks in other places and struggle with other places a lot more, like it's a very low impactful part of your project, but it's been really exciting seeing how many people are both motivated to do it, because it's the first time we've asked students to, and then seeing how many people, when they encounter problems, have figured it out. And a surprising number of people have actually figured it out on their own accord, and I think that's pretty incredible. So yeah, props to everyone for that. And yeah, I understand that. We spent almost 2 days on it. Don't want to lose marks. I get that. That doesn't change. Like, that's just a very human thing, right? Like, I spend... you should see what it's like when, like, it's everything, right? Like, last year I wrote some exam questions for students, and the tutors did it, and they were like, this exam's too long, and I was like, I don't want to... I put in all that effort. I don't want to just see it vanish, but, So, props for figuring it out. So, today we have 2 short lectures. The first one's kind of our last Python lecture, and in a lot of ways, this topic, iterators and generators, is not formally part of the... It's not formally part of the course. It's not part of the core of what we want you to know, right? And we kind of flirted with getting rid of it. We're like, it's not really critical. It's kind of interesting. In the end, we said, let's just teach it in week 10 as like one of these extra topics. And it does come up a tiny bit in the course, like in potentially the exam or like week 10 lab, but it's very light. And So in 20T3, Evan Colias, who's one of the lab assists, someone watching this now or later's probably got Kevin as a lab assist. He actually did a more extensive talk on iterators and generators as part of his Anatomy on Python talk, November last year. There's a lot of stuff in here, so this is kind of like if you want to understand a lot more about what's happening, then please go here. And today we're just kind of giving a very light run through it. So in Python, there is this concept called an iterator. And iterators are objects that contain a countable number of elements, right? So you can get an iterator for a list. So if I just take this code, we can just do this together here pretty quick. All right, we'll go into content lecture code week 10. Is this an iter.py? No, I'll make another one. Hello.py. So I've got this file here called hello.py. And basically, I'm going to print out animals, and I'm going to print out animal iterator. And we can have a look at what these two things are. Disk quota exceeded. Jesus. Ay. I don't know what this is. It's probably me, like, trying to auto-mark all your stuff. Nope. I don't know what this is. Let's see if this helps. A little bit. Okay. It's kind of nerve-wracking. Alright, let's copy this in. Print animals. Let me make sure I can save it first. Okay, I can save it. Did that work? Cancelled? Hello.py? Oh my god. Alright, give me a sec. I'm just going to do this in the class account. So we have a class account which we SSH into. This is where all the magic happens. I'll have to do this on command line though, potentially. So I'm going to open a animals.py or hello.py. And I will copy this in here. And then I will print animals, and then I will print animal iterator, like this. Okay. And let me just output that. So you can see the file, right? We got animals equals dog, cat, chicken, sheep. And I'm going to print out both of those, Python 3 hello.py. And you can see here that I get, in the first case, the list, and in the second case, the list iterator. Now, what the hell is the point of wrapping it in that iter object there? It's kind of strange. Basically, when you take an object like a list or anything and you turn it into an iterator, it is this kind of abstract object which is now iterable, in the sense that you can give it to someone who's expecting to be able to kind of pluck one element at a time, right? Like they want to like move through each element. So when, like, you've heard this term, iterate through a list, you're familiar with it. Like for I equals 0, for cats in animals or something like this. You can iterate through stuff, which means going through element by element. Now, lists by default are already iterable, but when you actually loop through them, I'm pretty sure Python turns them into this kind of iterator object. We can kind of have a look through some more examples like this. So let's say we want to make our own iterator, right? Because lists are already kind of iterators. They're iterable in the sense that if you try and iterate through them, Python knows to wrap it in this magical iterator object that you've seen here, like this. But let's make our own, just to try and really hone in the concept. So if we have a look at some code here, you'll see that we've got this class called squares. Now, if you remember from the classes lecture, we didn't touch on a ton. We kind of said classes consist of variables and then they consist of functions as well. In this case, though, we have three special functions that exist. And essentially, anytime in a Python class you see something that has like an underscore or a double underscore or a dundascore, it's usually some special kind of function that means something to a class. So in this case we have three, which is init, iter, and next. And there's also some others like string, for instance. Like you can define how a class gets printed as a string. And like I'll show you this example here as well. This is kind of annoying. I kind of want it. Let me just quickly try and figure out what's taking up so much space in my home directory. But anyway, this is a fun thing. I'm using 1001 megabytes, and I've got all these different files here. And folders are really hard to tell how big they are because they don't actually tell you how big the folder is. So if I want to see how big that public HTML folder is, I can do that. And it's 17 megabytes, which isn't very big. All of the Sublime folders are 34 meg. So that's pretty small as well. These files are small. This is the size in bytes, so all of these numbers are tiny. I can have a look at what my CS6080 or 6080 is. 528. So 6080 is half of my home drive now. And let's see what 1531 is. 1531's tiny. So what's probably happening here is like I've got all this crap. What? What's the other folder? Got all this crap in here, so I'll have a look. Let's have a look at it all. They're all roughly the same size. I'm just going to get rid of that cont and tutorials folder. Okay, so now when I run rquoter again on CSE, it says I'm using a lot less, hopefully. I don't know why that doesn't update. Did that work? I think it works immediately. I don't know. Cat hi. Hello? Hello? Oh my god. I don't know. Damn it. That's okay. Everyone hates me today. Let's just open up two terminals. So I've got my one terminal over here already, so I'll just open up a second one. I don't normally run out of disk quota, so sorry, this has caught me by surprise a little bit. I'm going to make a folder in the CS whatever folder. We'll call it week 10. I'll go inside week 10 and I'll do it over here as well. So now we can look at our files while we run them. So the simple file here is this squares class. So I'm going to create a file called squares. There's my class, and then over here I can run that class. Now, when I run this class, nothing happens. If I create an instance of this class, a particular object of this class, I'll call it S1 equals squares like this. I've created that kind of thing now. Now if I try and print S1, what happens is that it gives me a very literal definition of S1. It's like, well, you know, S1 is a squares, is a type squares object that was defined in the main file, and this is its memory address or virtual memory address. Oh no, everyone's losing their mind. Reese, did you miss anything in the first 15 minutes? Not really, no. Just a lot of finding ourselves. So if we want to actually print squares as a string, right, and not get that random memory address, we can actually use one of these double underscore methods as well to define that. So I can say, you know what, this is how I'm going to define what happens when I call it as a string. And if I do that, now when I try and print the class, it prints hello, right? Because because classes have these special methods. Now these other three methods are quite special as well, particularly these two in relation to iterators. This first one though, called init, is actually just the code that's run whenever you create an object of a class. So this init code is actually run right here, such that if I was to say print s1.i, right, because I is a property of the class here, what happens now is it will print 0 because it defaulted that to 0. So if I start this at 2, for instance, then it defaults it to 2. So it's kind of like the setup of this class. And remember, classes are just like structs without with functions and some other features. But what's quite key to this class, right? If I get rid of these three things here, if I try and print iter s1, so I'm trying to turn s1 into an iterator. So iter is a function that's built in to Python, and it tries to convert things to iterators. When I run that, I get an error. It says type error, squares object is not iterable. Basically, Python is like, I understand that you want me to take this class and turn it into something that I can loop over and iterate over, but that's just not possible. Yeah, just not possible. So we need to make it iterable. Now how do we do that? We give it these two special functions. Now I won't lie, I can't remember what iter is for, but next is kind of obvious in the sense that if you wanted to create a class like squares where you can iterate over it, in this case the behavior we want is to be able to iterate over squares and for it to basically give me all the square numbers like 2, 1, 4, 9, 16, etc. Then this kind of makes sense here, because what happens is for the iterator to work, it needs a function to call every time it iterates, right? Because every time you like loop through something as an abstract concept, you need like a new value of some point. What does init like a British person sound like? I don't even know how to say that. So in this case, what's happening is every single time that we would iterate through an iterator, it would call this next function. So because I've added these back in and I run this again, you can see that it works. It doesn't crash. Now I'm not doing anything with this iterator. In fact, like, have a look here. If I try and print the type of this iterator, we'll just get told that it's a oh, sorry, it did work. My bad. Let me get rid of that string function. So now we have an iterator of this type, and what that means is, if I'm not mistaken, we can actually now loop through it. So this one will loop forever, so I might have to put a sleep in here. Time.sleep 1 second, just because it will loop forever. So I'll import time, I will sleep every loop, and then we'll go. 9, 16, 25. So you can see what's happening here is, why is the first number 9? It's 9 because init starts at 2, because that's what we tell it. We tell it that the default value when we create an object is 2. And then every time we call next, we increase I by 1, which makes it 3. And then we return I times I, which is the square, right? So what's actually happening here is every single time this for loop is looping, it is actually collecting another value. And that value is being determined by this next function. Now, I don't need to put this iter here, because by default, what Python actually tries to do is when you do something like for I in something, it tries to get the iterator for you. You don't need to say, give me the iterator. It will just be like, I'm going to assume this thing is iterable, and I'm going to go and get it. So this will still work fine. So you can make any type you want iterable. Like, for example, if you create a class, right, just as another example here, called like marks, right, and you say, you know, def init, by default, you know, self.marks equals like 1 to, what's an example, like let's just throw a few marks in here, and we'll do it in a dictionary. Say like name Hayden mark 50, like that. Do that for a couple of marks. Who else we got here in the call? Ford and Reese, great. Ford and Reese. Now here's the thing, right? If I have this class called marks and I make a new marks object from that class, right? So that's like creating a new data type for a struct you have. If I want to iterate over that, right, and I want to get all the marks, right, I want to loop through all the marks, and I say for mark in M, print mark, what's going to happen is Python's going to say, sorry, but your class marks is not iterable. I don't know how to iterate through that, right? I don't know how to go through it. So we have to show it how to go through it. So let's copy what we did in this previous example here with the iter and the next. So we have a function called iter, and this one is just going to return self, and then we have a function called next, and this will help us know how to loop through it. So how are we going to do that? Well, in this case, what I might do is I might create another variable here called I for iterator, and I'll set it to be -1. And what I want to do is every single time someone calls next to get another, like to iterate through another element, I'm going to say self.i plus equals 1. So we'll increment that from -1 to 0 to 1 to 2 to 3 to 4 to 5, like that. And then I will say return self.marks I, because that's the particular list element I'm up to, mark. So that now when I loop through this, self.I, let me just get the self.I. Now when I loop through this, I'll get the mark. And now you can say list index is out of range. Okay, so let me just... So what's happening here? Well, one of the other problems, right, is that a iterator will just keep going forever, right? It'll just keep going forever until a time where you tell it to stop. So, you know, Google Python how to stop iterator. And I'm pretty sure you raised some kind of exception, right? So there's a built-in exception to Python where when you throw it, it basically tells Python to stop iterating. So in this case, I could say, you know what? If self.I is now greater than or greater or equal to the length of self.marks, right? If we've gotten to the end of that, then we want you to raise stop iteration. So that's a built-in exception. I don't have to do anything here. And this is what will cause it to just loop 3 times, like that. So this would be, for example, how you make one of your own classes iterable. Because, like, again, if you just try and loop through marks, the marks class is not aware that you want to loop through the marks, right? Because it's like, how do I decode that? Computers can't understand what humans mean when they want things. So that's kind of the crux of it. An iterator has to store the state of where it's up to. There's a few other kind of details here, but like largely we're not focused on the definition so much in this course. We just want you to just kind of be comfortable with the concept. So basically what this slide is saying is that there's kind of 2 buckets of things, which is you have here, that's the worst circle in history. So here you have like iterables, and then here you have iterators. And the idea here is that to loop over something, it needs to be an iterable type. A list is iterable, for instance, right? And an iterator, though, is something that actually has a next function, which generally is probably going to mean that it generates something. So if you have any kind of list type at all, you can iterate over it, even though it's not an iterator per se. Whereas like what we've created here is actual iterators because they have this next function here that determines what to generate next. So that distinction's not really super critical. The main thing we care about is like, you know, are you able to kind of conceptually grasp the idea of that if you want to make something turn into an iterator, like as in you want to, this is the perfect example, this marks class over here. If you want to make someone actually be able to do a for loop over it, then that's good. So some questions that have been asked is, didn't you say we don't do classes anymore? I said that we do a tiny bit of classes in the course. That's why we kind of teach it a little bit, but we don't really have any extensive expectation for students to use them thoroughly, right? Like we want a very basic understanding, but we don't really even touch the surface on this stuff. Great. Just reading through. Do we not need to catch the exception? No, so you don't catch the exception because it's basically like the for loop catches it for you. So you just raise the exception in your iterator because the for loop is like talking to that iterator. It's like, give me another, give me another, give me another. And it's just going to keep saying that until the iterator throws an exception, which is a stop exception. And then the for loop goes, oh, okay, I caught it. Great, thanks. I know to stop now. So that's dealt with by the for loop. Cool. Okay. Let's move on. So that was Iterators. Again, very light. If you want to learn more about them, you can go and watch Evan's talk. But in general, just what we've gone through today would be largely more than adequate to get through Lab 10 and any minor question that might come up on the exam. So the next part of this topic is generators. And generators are a little bit more interesting. The weird thing about generators is that you often can't really tell that something's a generator per se. So let's go through it, because I don't think it'll make clear sense until we do an example. So, what is a generator? Okay, well here's a problem, right? If you have a file, and let's make a file here called gen.py, and then you have a function, and that function is like getNumbers, and you want to say generate every square number up to, I don't know, 10,000 squared. So I'll start my I off as 0. I'll say for I, I'll say in my list of numbers is an empty list. For I in range of 0 to that number, list.append I times I, return I. Now this makes sense, right? If name equals main, print get numbers. Like this. Easy. Now if I run Python 3 gen, I get the wrong thing. There we go. I should get a giant list. Okay, great. And if I run it, let's do it even bigger. Let's do it 1,000,000 squared. Okay, this will go on for a while. So, or maybe we could even do something more complicated. I don't know. Divided by 5, divided by I. See if we can make something more complicated. That's just... Oh, division by 0. Oops. Let's go from 1. Division by 0. I don't understand. Oh, that I is pointless. I'm so sorry. I should know better than this. Okay, let's go. Right. So what's actually happening here, right? And I just want you to think about the flow. Is what's happening here is we call if name equals main, and then we call this function here, right? And if we want to iterate through those, for instance, for num in get numbers, and we print out every single one, what's actually happening here is that between when we call getNumbers, the function getNumbers is getting called. So you kind of have like, if you think about it like this, you kind of have like getNumbers, then you have like your main here. And what happens is that when main wants to loop through this, we start executing, right? We come into here, and then we hit this for loop, and then main says, hey, I'm going to call getNumbers. And then getNumbers has to go and get every single one of those numbers, right? Because it's adding them to that list inside the function. Every single one of those like 1,000,000 numbers or whatever. And then once it's done, it returns to main. And then main here will do what it does, which is it prints them out, right? Because it iterates through all those numbers that it was given, and then main prints them out like this. Does that make sense? So we got to create all these numbers first at once, because the function doesn't return until everything's created, right? That's kind of how programming works. And what generators are designed to do, to try and do, is to avoid this waste of time where instead of doing something like this, we can actually do something like this, where every single time one number returns, we like return numbers as we go and we print them out. So it's kind of like instead of doing things in like a chunk and then another chunk later, we just instead say we'll just grab one by one and like take them as they go. Because you could imagine what this is like with like a friend, right? Like say you're picking apples off a tree or something that you do on the weekend, and like someone's got a box of it, And like they could pick one apple at a time and put them in the box until the box is full, and then they could give you the box to unload the box. But it's a lot easier if every time you pick one apple off, you give it to them, right? Because you're basically going to get it done twice as quickly. So that's the idea of generators. And the way generators work is, for a function like this, rather than like returning only once at the end, a generator is kind of capable of doing little mini returns along the way. So this example generator here, of simple generator, call this one gen2, what this one is actually doing is it's actually returning 1 and 2 while the function is being called. So let me try and show you. If I then have a if name equals main, like this, and then I try and let's just do it for I in simple generator. I think this is how I call it. Print I. Take a look at this. So think about the logical flow of what's happened with this program here. I have tried to iterate through simple generator. And what's happened is simple generator has been called. It has printed out hello. It has yielded 1. Now what is yield? Yield is that mini return function I mentioned. So it literally is like a mini return. So it kind of returns that early so that this loop can keep going. Because how many times does this loop go through? It kind of goes through like a couple of times, like each time it yields. So the loop gives something to the inner part so it can actually work with it. And then simple generator prints the next line. And then it yields a second thing here, right? And then it prints another thing. So you can see that what's actually happening is the for loop is doing something before the function has fully finished. And that's kind of the power of generators, is that we can do things like if we don't need to wait for something, then let's not wait for something. So a couple of these slides I didn't write, but basically, intuitively, you can think of a generator as like a suspendable computation, which like I've just described to you as like it's capable of doing mini returns along the way, which I think might be a little bit more digestible for you. And then if you break out of the loop, does it stop generating? I guess so, probably. Let's try it out. I've never done that. I personally haven't had a massive reason to use these. Yeah, it does. So the break means it basically breaks out. So I assume what Python does is Python would have this ability to kind of like keep this like internal state, if you will, whereby like you call simple generator, right? It prints hello, and then it does this mini return of 1. And at this point, the function is in a state of like suspended computation, right? As in like it's kind of paused, and Python's tracking where it's paused. And then you print out your I because you got that mini return. And then what does a for loop do? Well, it goes back up to the for loop part. And then when you call this part again to get the next I, Python's like, that thing I suspended the generation of before, let's grab another one, right? So then it goes again and again. So in this case here, this for loop would iterate 3 times. Nothing would yield on the last time. It's kind of like returning nothing. But I could return something here if I wanted to. I could, yield 3. And I would get, hello, nice to meet you 3. So as you can see, it calling next on the generator executes it until it reaches a yield. So it executes this here, and then it reaches a yield, and then it stops, it suspends. At which point it is suspended or frozen until the subsequent call of next. Right? So it allows you to kind of like, chop through this thing if you want to get values early. It's very powerful for generating large amounts of numbers. So like here's an example here is a squares function. So in this case, if I wanted to get a squares if I wanted to get all the squares, this is a generator that like kind of never ends, right? But here I could say for I in squares, which will get me the square, and I want to keep going. If I should call this square. If square is greater than 1,000,000, break. Sorry for the inconsistent spacing. Otherwise, print square. So I've got this squares generator. It's a generator because it yields, and it will literally do a mini return every single time it generates a new square, and I will print that out until the square it gives me is above 1,000,000. Now you might think like, why is that? Why is that so exciting? Well, let's create like a dumb squares. Let's try this one. Dumbs. Actually, let's modify this function a bit. So, what I want this one to do is, let's pass in the I. So we'll say that the squares, we'll call it squares generator. Squares gen. And it takes in an I as whatever 0, and we'll say while I is less than 100,000, we're going to do that. So now we don't need this break. I can literally just say, yeah, let's just loop, sorry, I've done this the wrong way. Highest equals 0. I'm a programming genius, apparently. Okay, so we set I is 0, we loop while I is less than highest. We keep going, and we yield every time. So now I'll say 100,000 like this. So now this should also work. Nope. Squares gen, because I changed the function name. Sorry, I think it's meant to be that. Squares gen. Okay, so I get all those numbers. Now, let's have a look at an alternative version, which is where we don't use a generator and we actually generate all of them in advance. So I'll say like squares normal, and I'll say the highest is 0, and we'll do a similar thing to what we did before, where I say, you know, I got this empty list for I in range up to highest, list.append I times I, and then we'll return the list. Right, so we'll do the exact same thing here. We'll say for square in squares normal up to 100,000. Print square. So these two things will be identical. Right, it'll print out, bam, and then it'll do it again. Now the question is, which one's quicker or slower? I think I did too many zeros there. There we go. So we got one, and then done. So what I'm going to do here is I'm going to use the time command in Linux. So if you put time in front of anything you run in Linux, it'll actually tell you how long it took. So if I do that, it'll tell us at the end how long it took. Okay, so that took a real time of 2.639 seconds. Now what I'm going to do is I want to contrast these two. I don't actually know if we'll see the benefit at this small scale, but let's see. Let's see how long it takes to do the generator one. Okay, 1.207 seconds. Now let's try the normal one. So if this is slower than 1.207, you can see that we're losing time in first having to generate the numbers. 1.3, right? Now, this is a very bad test for a few reasons. It's like, it's a really small scale, which isn't great, because like normally these things you notice at a larger scale. If any of you are doing 2521, it's like, whether an algorithm's n squared or n, it's not going to make a difference if the n is small. The other thing is that Python, like most languages, will do some optimizations by the interpreter, right? Like, and I don't know what they are because I'm not a Python compiler developer, but benchmarking is a really hard thing to do with languages, because sometimes languages do things. Like a language will literally look at this and be like, hey, they're literally just making a big list. I can do that like that. You know, like it can skip things sometimes. Like I've seen this happen where like if I don't know what language I remember, but like there was one language I remember where if you have a function that's called that doesn't like take in any parameters and it doesn't return anything, sometimes like a certain compilers will just optimize the function away. So if you call it and it isn't literally doing nothing, the compiler will just be like, we'll just get rid of that. Because it's slow and it does nothing. So it's really hard to benchmark, but you can kind of see, try doing only the first 100 elements of it and then compare performance. Will that be better? I feel like 100 would be worse, wouldn't it? Let's do the normal one first. 0.13. 0.14. In that case, the generator's slower. I mean, these change every time too, right? 0.13. So you can see that's like varying by quite a reasonable amount. Let's try really big numbers. Let's do 1 million. This will take a little bit. So let's try the generator for 1 million. It's also hard to tell because when you print things to the terminal, that's actually a huge slowdown. It might even be slower than writing it to a file potentially. But hopefully we're like most of the way done now. I hope this isn't like an order of magnitude out and we have to keep waiting. Okay, 24.5 seconds. And again, we really should have run this a few times, but 24.5 is where we start. What the fuck? Yeah, I don't think we're... Yeah. One of the problems with doing tests on small numbers is because a lot of processors are actually really fast at doing like small things. 23 seconds. Yeah, see that one, in that case, that one found it quicker. It's really hard to tell. Like you'd have to do a more controlled test. But generally, so there's a... Oh, right. I see. Oh, sorry. I see what you're saying. Sorry, Miguel. I understand what you're saying now. Yeah, so you beat me to the punch. That's what I was getting to next. So in a general sense, you're going to see some minor improvements because of the fact that generators will return in real time. Again, that's super contextual. But the main benefit of it, right? Well, another benefit of it is that sometimes if you are generating a large number, you might not want that entire number. So let's say, for instance, that you want to break out of this once the square is greater than 10,000. So if the square is greater than 10,000, you want to break. Now, the benefit of our generator is that because the generator is generating one square at a time, the second we call break on the loop, the generator will have only generated up to that number at the time, right? So we're not going to bother having to generate all those extra numbers. In the second case, though, because squares normal is not a generator and it generates all the numbers, we're going to generate all million squares first. Then this function will return for us to iterate through. So basically we're going to generate like 1,000 times more numbers than we actually want in this case. So if we would compare the time difference between these things here. Alright, we'll do this one first. Really? Okay. By the way, this demonstrates to you just how slow printing is in terms of real-time usage. Because you see that one was like 0.2 seconds instead of 25, even though we haven't really done too much different, because we start to generate 1 million squares, which is the mathematically, I wouldn't call it complex, but that's the more complex part. So that's 0.3 seconds. And if we try this one, hopefully it's quicker. Seems to be a little quicker consistently. Let's run the other one a few more times. Do you see that? See that little bit of extra lag that's happening? Like that little pause? So the actual printing of the numbers is quite quick in this case because we're doing like, I don't know, 100 numbers. Probably 100 numbers. Yeah, about 100 numbers. So the printing's really quick, but that lag you feel before anything happens, that's the actual squares normal generating all those numbers, which is taking forever because there's 1 million of them. Cool. Great. Just having a look here if we want to go through any of this today. So this last slide is basically a little tidbit, which isn't really, this is more just fun information for you. Basically, one thing you would have noticed that you're doing between C and Python is the use of libraries, right? Like in C, you weren't using many libraries, whereas in Python, you're using this and that and time and sleep and date time and everything else. And in a lot of modern software engineering, Python and everything else, we use a lot of libraries. And this is really helpful because it makes our software better, because if your software doesn't work, there's a high chance it's going to be your code, not someone else's code. given the fact that libraries are generally written by very experienced developers. So there's a lot of pluses for it. And a lot of libraries like Flask, Python, a lot of these libraries are not managed by like the Flask company. They're often managed by random groups or certain people. Like Flask here is actually, I don't know what the hell Palettes is. The palletsprojects.com. This is probably some open source community. Collection of Python web development libraries that were independently developed by Arm and Ronacher and later blah blah blah. So basically, like literally, it's like, this is the cool thing about software, right? It's a whole bunch of randoms. When I say randoms, I mean like, you know, extremely generous and intellectuals. But they're not like again, there's no Python company, right? Like you don't work for Python, you don't work for Flask. A lot of these things are open source communities, and you see some of these similar libraries here, right? Like Workzoid and Ginger. Anyway, the point is, these are all real libraries on GitHub, like GitLab, that you can go and look at. Like Flask is just a whole bunch of Python that's, you know, very well documented and very extensive. So whenever you do a pip3 install, you're actually grabbing all of these files. A particular version of these files, of course, but you're grabbing all of these files. Now this is great because it means that, like, you think about the scale and size of your project in this course, it's massive given how little code you've written, right? Even if you feel like you've written a lot of code, you haven't written a lot of code for what you've accomplished. One of the downsides, though, of libraries, and one of the like only downsides, is that it does create a lot of surface area of your application. Like a standard Python project like yours could rely on dozens and dozens and dozens of libraries. One example is that there was this library in JavaScript called LeftPad. I don't know if it's still there. And LeftPad is no longer used. But basically, it was a it was a library where you would give it a string and how much you wanted it to be padded on the left, and it would fill that space there. So if you said left pad foo of 5, you get 2 empty spaces. If you said left pad foo bar of 6, you get no empty spaces, and you could, you know, it was a way to kind of control the width of strings, right? It's now built into the language itself, but I mean, you can see it's still downloaded 3 million times a week, right? There's like 3 million people pip3 installing it. But the problem was, what happened was there was this big disagreement, and basically this person took down the library. They were like, nope, I don't want anyone using it anymore. And because that library, even if you weren't using that particular library, right? Even if you hadn't pip3 installed that library, you might have pip3 installed something else that uses that library, right? Or something else that uses something else that uses that library, because most of your Python applications are just massive webs of dependencies. And this is just something that you need to be aware of as a software developer, because your code is simple. Using libraries is a good thing. You might think, oh, using other people's code sounds kind of dangerous. Well, it's only as dangerous as, like, it's bad. And again, which do you think is more likely to be buggy? Your Flask server that you write with the Flask library, or this like fairly experienced community of Python developers who are all code reviewing each other, and like 21 people clearly working on this? You know, and for some of you in this call, in this lecture as well, like some of you will end up being massive contributors to these libraries one day. Like it's a common thing that you'll see happen at a lot of big tech companies too, is they'll carve off time in your pay if you're, you know, really experienced and part of a community to like look after this stuff, because you'll find a lot of these people will be like current I don't know any of these people obviously, but like yeah, so this person is just a intern. This guy's very young. David Lloyd, I don't know if there'll be any information about. I mean, sometimes these people, Python engineer, core developer, don't know. But like some of them work at tech companies. Some of them are just like retired and like they love what they do. It's this crazy weird community of people that keep everything alive, which is very strange when you think about it, right? Like think about this. It's like when you write software to put on planes to control things like the wings of planes, It's like that's written on Linux, right? Who wrote Linux? It's an open source project. Like things that literally keep the world afloat are based on this entire web of like essentially volunteering effort and people trying to look after each other's code. So anyway, I was just killing some time till 1 p.m. This was the entire library. This was the entire module. It was that simple. Someone just wrote that and they took it down and they broke a whole bunch of stuff. So you just have to be careful with that. Anyway, you can do more reading if you'd like to, but that's about it. So we're going to take a 5-minute break. Then when we come back, we'll talk about building an MVP, which is just a very, very short lecture where I just talk about some things specific to if you if you have an idea about a cool app you could build with some friends, how you go about it in a non-technical sense. So let's take a 5-minute break, and actually I should send you the easy poll thing. One sec. Okay, let me just grab it. How is iterators and generators? Save. Okay, great. Here's the poll. All right, 5-minute break, and then we'll get back into it. Okay, chat then.